and we during these lectures we will study probability distributions, probability measures in infinitely dimensional spaces. So first of all, we have to understand why we need to study such a complicated object. Because the main object of our investigation during these lectures will be forward. We will have some Banach space B with a norm. We will have a Borel sigma field here, and we will have a probability measure mu in this space. And you already know that such kind of object are complicated itself. For example, when we study probability measures on the usual Euclid space, we have a lot of interesting and difficult questions, like absolute continuity with respect to the back measure, like structure of characteristic functional and possibility to recover the measure using this characteristic functional. When we study Borel sigma field itself, it also leads to very difficult theoretical questions. For example, maybe you know from the usual course of probability that there are some sets which are not elements of Borel sigma field, but it is complicated to build such set by hands. So you see that this also is complicated object. And when we discuss the Banach spaces, it also itself a very complicated object, even if we try to check whether some normal space is complete or not. For example, when we try to check is it separable or not, what is the compact set in this space, what is the consequence of non-local compactness in this space, and so on. So it naturally arises the following question: why I am proposing a course where we have a lot of complicated objects from theoretical point of view? Really, do we need such object when we study probability theory, applications of probability theory, or application of stochastic process? So today, let me begin with the example which will show us that this object can arise naturally, and that we have to study it in order to get a real answers in applications problem. So let me recall you the following situation, which arises very naturally in statistics. Suppose that we have x1, xn, the independent, equally distributed random variables, and we asking about the question: do they have distribution function f? So this is a question from statistics, and we know the answer. We know the algorithm. one of widely distributed when f is continuous. Suppose that f is continuous. I also will suppose that f is strictly normal. Then what we can do, we can apply Kolmogorov-Smirnov criteria. Let me tell you. We can consider 1 over square root of n sup with respect to 0, 1. Here is the such difference sum from k equal 1 to n, indicator that f of xk is less or equal to x minus x. So we consider such functional. You see, here we just apply our hypothetic distribution function f to our elements of time series xk, and then we consider such difference minus x. X is taken from interval 0, 1, and calculate the sup. And the usual textbook from statistics say us, this is well-known distribution, and this is Kolmogorov-Smirnov criteria. So we, if we hit this distribution, then it must be like dn, and we know it, and this is Kolmogorov-Smirnov criteria. Yes, then we just can take tables of this distribution and then do something. But let me ask you, do we know why it happens? What is it really? What is it? So let us try to understand how one can construct such criteria. And what we can suppose to have as a distribution of such random variables. Let's begin. First step, maybe you know. So if I have random variables x1, and if it has distribution function f, then it follows that f of x1 must have uniform distribution. Is uniformly distributed. Uniformly distributed on 0, 1. Okay. Then let us take this uniformly distributed random variable. I will from now denote it by y1, y and so on, y. and consider such random values. Then what will be the sum? 1 for n k equal 1 to n. Here we have indicator of yk less or equal to x. This is again well-known object for us from 2 points of view. First one, this is empirical distribution function obtained from IID sequence of uniformly distributed random variables yk. So I can say that for fixed x, this sum, due to the strong law of large numbers, goes to x when n tends to infinity with probability 1. We know this. This is the one point of view. Another one, that this is function. So another one, it is function. 1 over n, sum k 1 to n, indicator yk less than, in order to emphasize that this is a function, we just put here comma and say x belongs to 0, 1, and we get a function. And maybe it goes to function x in some functional sense. Okay, it's true. It's true, and it can be checked. This is general fact. For example, you can find it in statistics textbook that empirical distribution function with probability 1 weakly converge to real distribution function. In our case, a real distribution function is x. Yes, is x. It is continuous, and it is also a good exercise, also from statistics. So I don't write it. It is not exercise from our course. It is exercise from statistics that it converge uniformly if the limit function is continuous. So what I can say is that here we have uniform convergence to x on this interval when n tends to infinity. When we have such a fact, we again have two reasons to go further, to do next step. The first reason is our knowledge of student course of probability, because in the usual student course of probability, we have not too many probability laws. One is the strong law of large numbers, we already mentioned it, and actually second and last one is in the usual course, it is a central limit theory, which gives us the behavior of the deviation in the strong law of large numbers. So what one can say, if we now consider the difference if you now consider the difference of these two things, this sum minus x and we multiply it by square root of n, so we consider such case, minus mx here, then it has a limit in weak sense. Then we know that it weakly converge. I will denote it by such a symbol. It means convergence in distribution, weak convergence. It weakly converges to Hausche random variable with 0 mean and a variance which is given by expression x1 minus x. Central limit theorem gives us the behavior of this difference in such case. But what is bad here? That x here is fixed. We discuss the behavior of the sequence of normed and centered sums of random variables. So we want to understand what happens for different x, because this result is contrasting with the result which we mentioned, that this empirical distribution functions, here we have yk less than x, uniformly converge to x. So maybe one can ask about the behavior of this deviation, not only under fixed x, but taking some distance between two functions, And also maybe one can mention that when we just have the difference, let me, I can use this one, and consider this difference as a function when x is taken from the interval 0, 1, then these functions have a limit. And to obtain this result, we need the understanding. What is the random function? What is the convergence of random function in distribution? Because if we have the only convergence in distribution for fixed x, one cannot expect that for all functions we will have much more strong convergence in probability or almost sure. So we understand that now we need the notion of weak convergence of functions in some functional space. More, suppose one can check that this is conversion in distribution to some function. Yes. Let me for a moment denote this function by xi of x. Then what I can say that xi is a random function. Also, what I can say, maybe I know something about its distribution because we remember the central limit theorem, and it gives us not only the fact of convergence in distribution, it gives us the statement that the limit is Gaussian. So maybe I can suppose that this random function is a Gaussian function. Finally, maybe I know correlation of this random function. So I will have some Gaussian limit. And what is the distribution which we mentioned before? This distribution is equal to the distribution of supremum 0, 1 psi of x. So the nature have a question. What will be a distribution for Gaussian function? It's supremum of its absolute value. But what is the absolute value, the supremum of the absolute value for the function? This is so-called a uniform norm of psi. So we have normed space of bounded function or continuous function. And in this space, we have a random function. We have central limit theorem in the Banach space of normed functions. And we apply this theorem to empirical distributions. And we get the answer finally as a distribution of the norm of Gaussian random function or random element in Banach space. This is only one example which gives us knowledge how we can use Banach valued random elements in order to get some statistics. Yeah. So we just thinking in a way related to infinite dimensional space. In our case, related to functional space, in order to get the description of the limit distribution. And now our problem, if we want to find this distribution, becomes to be purely analytic. We just have some random function, some random element in Banach space. We know its distribution, we know its covariance now. It is Gaussian known covariance, and then we want to have the distribution of its norm. And it occurs that we can solve this problem in some cases. So this is just one example of way of thinking in probability theory, where one can apply infinite dimensional spaces and random elements there, and conversions in these spaces, reconversion in these spaces, and so on. During our course, we will see another motivating examples. But now it's time to start, and let me start with the examples and discussions what is the infinite dimensional normal space. So today we begin with the examples of infinite dimensional normal spaces. Maybe it's good to start with the general definition that we have B is linear space if here is the commutative operation sum. So for all x and y belonging to B, we have sum x plus y belonging to B, and this operation is commutative, have 0, so there existed 1 such that 1, 0, such that x plus 0 equal to x for any x. There also there exists a unique inverse operator with respect to this operation, inverse element with respect to this operation. So minus x plus x equal to 0. And it admits also operation of multiplication on the scalar. So for every alpha equal to r and every x belong to B, we have alpha x belonging to B, and we have distribution laws of multiplication with respect to this operation x plus y. I don't pay attention to this algebraic stuff because all we know what is. So I suppose B is a linear space, and now I will suppose that here we have a norm. So norm, I will denote it as usual by the symbol. This is a function which is active from B to 0 plus 50 with the property Z. The one. Norm of x is equal to 0 only if and only if x is equal to 0. Another one that more satisfied Bernoulli inequality. Norm of x plus y is less than norm of x plus norm of y. And another one is that norm of alpha x is equal to absolute value of alpha multiplied the norm of x. So if B is equipped by such function, then we will say that B is a normal space. Now we have norm B. A linear space, and a final step, let's suppose that if B with this distance is open, so that any Cauchy sequence have a limit B, then B is called Banach space. Then B is called Banach space. We have a very interesting partial case of Banach space when norm is generated by the integral. Sometimes it happens that we can define the binary operation, which is active from B multiplied with B to R, such that it is symmetric. Such that it is positive x is greater or equal to than 0, and equality is again happen if and only if x is equal to 0, such that it is linear with respect to both arguments, so alpha x plus beta y multiplied z equal to alpha x plus xz plus beta yz. In this case, one can say that we have a scalar product on our space, and one can define the norm of x as a square root of x. Then, in this case, and if it is Banach, then we can say that B is Hilbert space with this scalar product. In this case, B is Hilbert space. We will start from the example of Hilbert and Banach space. So let us start. First of all, consider Hilbert case. Suppose that H with a scalar product is a Hilbert space. Then structure of H heavily depend on two things. The first one is dimension, and second one is separability. First of all, about dimension. What is dimension? Dimension is the cardinality of the largest linear independent system of vectors in H. Yes? So dimension of H is cardinality of largest linear independent system in H. Here I already wrote a very complicated sentence. Why? I say largest, so it must exist. The first one. Another one. For example, we have two largest systems in a sense that we cannot add any element, any element to this system to remain linearly independent. Why they have the same cardinality? This is a very heavy The first one can be solved using Thorne lemma, and second one also use transient induction to hold it. So this is a big problem, but we will not pay special attention to this problem. I only mention that this is non-trivial sentence here, written here. And if you want to pay attention to it, please check the very good book of Paul Halmosh. Linear finite dimensional linear spaces. Finite dimensional linear spaces. You can find a good discussion there. Or, also, I will recommend other books during our course where you also can find the discussion about these two questions. But let us suppose that we know that there is lattice, that they have the same cardinality. And let's come back to our examples. As I said, dimension is one of the important characteristic of the Hilbert space. First of all, suppose that its dimension is less than infinite, so that it has finite equal to. Let us take the system which is linear independent and have cardinality n in this space H. So take such a system which defines the dimension. Okay, so F1, Fn are the elements of H and their linear independent. Linearly independent. For any case, I will recall that it means that such a linear combination k equal 1 to n alpha k fk is equal to 0 if and only if all alpha k's equal to 0. Also, it means that if I consider any other, because we mentioned that this n is the dimension. So what we know that if I consider any x which belongs to our space H, then this system is linearly dependent. I omit what linearly just for simplicity. To this fact means that one can find non-trivial linear combination of these guys which equal to 0. So we have some k equal 1 to n beta k fk plus gamma x equal to 0, such that it is non-trivial. So some betas are non-zero, or maybe, and some gamma and gamma. Let us check it more precisely. Can it happen that gamma equal to 0? No, due to this fact. And we already said that this is not trivial linear combination. Somewhere among the coefficient is non-zero. Due to this, one can say that gamma is not equal to 0. Then what I can do, I can divide everything on minus gamma and get finally the following relation, that x is equal some k equal 1 to n. I will say, for example, delta k fk. And so we proved that now x is a linear combination of our elements of fk. Moreover, this representation is unique. It is trivial. If we have another one, delta k prime fk, then the difference must be equal to 0. And coming back to the condition on our elements f, we can see that any delta k is equal to delta k. So what we can say, that any x can be uniquely expressed in as a linear combination of our elements. In a linear algebra, people say that fk organize a basis for our finite dimensional space x. But what we have to do now, we have to relate this basis to our scalar product, because it is good to have a right understanding how to get this coefficient delta efficiently. Can we do this? Yes, we can. And I will show you two ways how to do this, because it is important for us in the future, and during this consideration we will get an interesting object. So the problem is how one can efficiently get the coefficient of the expansion of x along the basis. How one can find this set delta k. And now Hilbert structure will help us. Let's do it. So I will consider the following. I will consider the following scalar products. For any k, excuse me. Добрый день. Знаете, у меня сейчас лекция, а потом семинар. Если можно, я перезвоню вам по этому телефону в районе часа дня. Да. For all k, which is equal 1 n, we have the following expression. X fk, I just multiply of x on the element of basis, is equal to sum from j equal 1 to n alpha j excuse me, delta J multiplied by scalar product Fj Fk. Okay, so we have such linear equations. Yes, we see that now our delta satisfy linear equations with Fk. With such a matrix, here is a matrix, and such a right side, and this is equation which contains n variables and exactly n equations. So one can try to apply Kramer idea to get the solution. Yeah? Let's do it. First of all, let us consider a matrix of equation. Yeah, just forget about it. Matrix has a very interesting type, and even I will use a special notation for this matrix: F1, Fn, and it has a form F. It does not matter. It's symmetric. Fk, Fj, and Kj is equal 1 to n. It is called gram matrix or Gramian matrix. Constructed from F1 to Fn. Okay, so we have such a matrix, and one can ask, is it the matrix which is non-degenerate or not? So let us think about determinant of this matrix. I am going to show that this determinant is greater than 0. How one can check? Let us check that this matrix is non-negative. It's already symmetric. Yeah? Let us check that gram is a non-negative matrix. Really, suppose that I have such a quadratic form. Kj is equal n1 to n. Here coefficient Fk, Fj, and here is alpha k, alpha j. Excuse me, alpha j. What I need to prove? I need to prove that this is non-negative. But by linearity, it is very easy to see that it is nothing else than the norm of sum k equal 1 to n alpha k Fk squared. So it is non-negative. Moreover, we already said that Fk is a linearly independent system. From this we understand that here we can have 0 if and only if alpha k is equal to 0. So we understand now that if we have equality, then we have all alpha k's equal to 0. It means that our gram matrix F1 F, N are strongly positive. It means that its determinant, I will do it, its determinant is also strongly positive. So we know that now we can apply Kramer procedure to get coefficients of the x in the expansion along the basis. This is one way how we can relate basis in Hilbert space, finite dimensional Hilbert space, with the scalar product. Now one can check that every x can be uniquely expanded, as a sum alpha k fk, and this alpha can be obtained from the solution alpha j will be equal. Here we have determinant of gram f1 fn, and here we have determinant of I will put here gamma j f1 fn x. Yeah. So we just substitute fj by x and for the row, or because of symmetry for the one line, just for one line. Okay, let me put here prime. It is not round determinant of this vector. It is substitution from the Kramer procedure. Okay, so we know how the Hilbert space is constructed, and what is remain is to get simplest basis. What I mean simplest? Maybe when I talk about this Kramer procedure, some of you came to me, oh, this Kramer and so on. But we have a good case when determinants can be calculated very easy. This is a case when this is diagonal identity matrix. In this case, determinant can be calculated easily. So we have to understand that there exists a good basis in Hilbert space. We will do this on the next lecture. Today, this is all what I wanted to present to you. And for my seminar, I will send a link just now. Okay, thank you for attention.